So I wanted to do some examples from section 15.6, triple integrals. Uh, I'm just going to set up these integrals because solving them I think is pretty straightforward. So go ahead and pause the video if you need to and read number 12 here. Went ahead and graphed it. We have we have the point. This point here is, let me do this in blue. Pi 0, 0, and then this point here is 0, pi 0. So we have this triangular region down here. And then we have z equals x, this plane above it. And we are integrating, we're doing the triple integral of sine of y dv over e. So e is this piece right here, kind of, let me do this in blue. It's this piece in here between these regions. It's the blue piece. So it's the solid. This dv here is a little volume piece of E, the solid. This is a solid there, all right? And we are integrating sine of y over the entire solid, both inside and out. So the hardest part is setting it up with the integration. So what I will do is I will use dz, dy, and then dx. So we look at what's going on in the z direction. In the z direction, it looks like we're starting at z equals 0. And the highest point it gets is z equals x. So that'll go to x. Now it makes more sense. Now, well, it doesn't make more sense to do dx dy. We'll do dy dx. So once I'm done with this dz piece here, this dy dx, I see what's going on in the yx plane, xy plane. So you have this point, this line here. I'll do it in blue because it's in blue in the original. This is pi, and this is pi. It's this line right here. So that's the line y equals negative x plus pi, or y equals pi minus x when you do the math. So y goes between 0 and pi minus x. And then x will go from 0 to pi. The last one always has to have constants. These are both constants, always constants. And then the second to last one that you do is going to be the just normal integration. It's the whatever figures in the xy plane. The first one that you integrate, the most interior one, is what's going on in the z direction. Or if it's more things are happening in the y direction, that'll be what's going on in the y direction, whatever. We'll do an example of that in just a second. So that's number 12. Let's try number 13. So 13 is similar. You have z equals 1 plus x plus y, so that's some plane in the z direction. And then you have something else going on in the xy plane. So z equals x plus 1 plus, I don't know what that is. It's some plane, all right? And it doesn't really matter necessarily what it is per se. You just have to, you can work with the integration regardless. It's not horizontal. It looks like something else. I'm purposely not graphing it correctly because it for this problem, it just doesn't matter what it is. Because really the only thing going on in the z direction is is just that plane. So my triple integral, so it'll be triple integral of 6xy, that dv piece, the dv piece will be, we'll do dz, then dy dx. In the z direction, it's 0 to 1 plus x plus y. Now, for the last two, we look at what's going on the xy plane. So in the xy plane, what we have here is, this is y equals square root of x, and then that's not quite that high, looks like that. And then x equals 1, that's here. Y equals 0, that's here. So it's just this piece here. So what it looks like is this. And we have the x, y plane. Here's y, here's x and z. So this piece right here is y equals square root of x. So in my integral, this will go 0 to square root of x, and then x goes from 0 to 1. And that's it. That's your integral. All right, let's try number 14. All right, so what we're going to integrate is triple integral of x minus y. So this is some function that's acting on the object E. It's on the solid E, inside and outside. It's going to be a function that's defined on E. dv is a little volume piece of E. It's basically the volume of E, but little pieces of it. It's enclosed by two surfaces. When you look at z equals, this is x, this is z, x squared minus 1, that is this, and then 1 minus x squared would be this. Well, a little higher, like that. So when you consider drawing this first in 2 dimensions, all right, you can, then blue is the 1 minus x squared. That's this one here in light blue. And then in red, that's the x squared minus 1. So what's going on in the z direction is whatever is in between here. That's what is in between here, right there. All right, so what I've done is I've drawn this in 3 dimensions. It's z equals x squared minus 1 is in red. So that's the paraboloid move. It's a parabolic cylinder. Notice that there's no y component in there, so we just draw it straight out from in the y direction. So it's like taking this red one and drawing it straight out in the y direction. And then the blue one's upside down in it. So you don't really have to be an artist and figure out how to draw this. So, but it does help to know kind of how to do it though. Let me put the x here. So we need a triple integral of x minus y dv. So I'm going to do dz first. Z goes from x squared minus 1 to 1 minus x squared. That's what's going on in the z direction. Now I consider for the outside integrals, this is going in the what's going on in the xy plane. So in the xy plane, you can see that in the xy plane, that's where z is 0, x and y. So where z is 0, we're looking at this, where z is 0, x is just plus or minus 1 in either one. So it's going between 1 and negative 1. Y goes from 0 to 2. 0 to 2. So it's going, the figure in the xy plane is this, 1 to negative 1 and 0 to 2. So it's just this right here. So x is going from negative 1 to 1 and y is going from 0 to 2. So that's what we put right here. So it'll be dz and then dy dx. Since it's a rectangle, it doesn't matter which one comes first because they're just constants anyway, and it's not going to be easier one way or the other. And there you have it. If you look at the geometry of this right here, it's not so obvious what's going on in the xy plane, but just look at what's given here, and you'll see that when you just make z equals 0, and that'll tell you really kind of what's going on in the xy plane. All right, let's try 15. All right, so here's 15. So if you want, pause the video and read 15. We're essentially taking the integral of the triple integral over of y squared over this solid tetrahedron. So what I did was I labeled the points, and now it's a tetrahedron, so we're going to connect these points up. Not good. Like that. And it's this tetrahedron right here. This could be a little better. So what you need to do is consider, now we need to figure out what's going on with the z direction now. So this is the tetrahedron right here. So our triple integral, okay, so this is what's going on in the xy plane, and then this is what's going on in the z direction. So in the z direction, it looks like I'm going from z equals 0 to whatever this plane is. So we got to figure out what the plane is. So I'm going to pause the video and figure out that real quick. So what I need to do is find the expression for this plane, the plane that's formed by B, C, and D. It's this plane, basically the triangle. But it's a plane that whose intersection with the first octant is this triangle. So what I did was I formed two vectors that are on the plane, and now I formed the cross product of them. And then the cross product of them will give me a vector that is perpendicular to the plane. So this is going to give me 4, 4, and then 4, 4, 4, 4. So that's my n vector, and I can actually make that, that's a multiple. I can make that 1, 1, 1 if I want, because I just need a vector that's perpendicular to it. Any vector that's perpendicular to the plane is fine. 4, 4, 4 is a multiple of 1, 1, 1, so I'm just going to use 1, 1, 1. And now I use my formula, first one times x minus, and then I'm going to pick a point on the plane. I'm going to use b, and b was 2, 0, 0. X minus 2 plus 1 times y minus 0 plus 1 times z minus 0 equals 0. This I'm using n dotted with r minus r naught equals 0, where n is the vector, remember, a, b, c. In this case, it's going to be the 1, 1, 1 dotted with r is x, y, z, and then r naught is a point on the plane itself, x naught, y naught, z naught, like that, equals 0. All right, so this is what I'm using. So I got x minus 2 plus y plus z equals 0. And so it looks like z is equal to 2 minus x minus y is the equation of that plane. So what's happening in the z direction is it's going to go from 0 to 2 minus x minus y. And so we plug in that y squared piece, which is, the actual function itself. This is now dz. And now we figure out what's going on in the xy plane. Well, it's the projection of the surface into the xy plane. So that will be BC. And BC looks like it's, so in the xy plane, BC, here's B and here's C up here. This is 2 and this is 2, so that's y equals 2 minus x. So I go, y is going from 0 to 2 minus x, and then x is going from 0 to 2. And so that is my answer right there, and you just evaluate it from there. This is dx. And that's number 15. Let me see if I can find one that's a little harder. All right, the one I've chosen that's a little bit harder is 22. So it says use a triple integral to find the volume of the given solid. So the volume will always be the triple integral just dv over E. All right, so in other words, this is a 1 here. And it's kind of the similar thing to what is the area of a figure in 2 dimensions. It's dA over D, where this is a 1. So it's kind of similar to that. Anyway, the cylinder I've drawn in red here, that's the cylinder x squared plus z squared equals 1. Maybe not the best cylinder you've ever seen, but basically it's you just draw your circle in your xz plane, and since there's no y coordinate there, you just continue it out in the y direction. All right, and then the planes is y equal -1 back here somewhere, back there, y equal -1, that's that plane back there. And then y plus z equals 4, that starts out to be a line in the zy plane. So it's z equals 4 minus y, which is basically this line right here. And since there's no x coordinate, you just pull it out into the x direction, so that's this. I guess I could have drawn it more like a slope of 1, but there you have it. And so that's this plane. And so it's the mixture of these two. So it's the cylinder here. It's the cylinder here, but then it's cut off by the plane there. And so what you have is this figure down below, which I've drawn, where the blue plane is what's right here. All right. And it goes further back. So, because it's y equal -1, so y equal -1 is back there, yeah. All right. So this is essentially what we have. Now, so we have to find the solid enclosed by this. All right. So we do triple integral dv. All right. What's going on in the z direction? Well, we're actually going to do this problem a little differently, because really what's happening is more what's going on in the y direction. So I'm going to do dy and then maybe dz dx like this. So in the y direction, it looks like we're going from y equals -1 to whatever this thing is. Well, that's just, I'm going to have to change this around. This will now be y equals 4 minus z. Yeah, because if you try to think of just the z direction, up and down, up and down, up and down, it changes starting here. So if I just go in the y direction instead, it's the same throughout. So I'm going to do y direction now. So it looks like it's going to y equals 4 minus z. Yeah, 4 minus z. And now we look at what's happening in the, as this whole thing is collapsed into the xz plane. So in the xz plane, we've basically just got this circle. X squared plus z squared equals, let's see here, what did we have? Ah, it was 4, not 1. It's 4. This is a 4. Okay, so that's fine. So x squared plus z squared is 4. And so this here will be that. And I'm going to convert immediately to polar coordinates. So this will be 0 to 2 pi, 0 to 2, integral -1 to 4 minus z, and then dy, dz, dx. All right, so I'm going to go ahead and finish this one. Oops, not dz, dx, it's rd theta. rd theta. So there's no theta involved in this. Well, I'll just leave it 0 to 2 pi, 0 to 2. And now dy will be, it'll be y from -1 to 4 minus z. Now, z in this case, it kind of functions as the y would here. Remember, we have x equals r cosine theta, and then y equals r sine theta. So sine theta. So z in this case will be 4 minus r sine theta. So it's 4 minus r sine theta. So we do r d theta. And so we get integral 0 to 2 pi of 4 minus r sine theta minus a minus 1, so that's plus 1, so now this will be a 5 sitting here. And then r d theta, integral 0 to 2 still. So now I take that integral 0 to 2 pi, and this will be 5r minus r squared sine theta d theta, integral 0 to 2 still. And now I take the integral of that. So it would be 5 over 2 r squared minus 1 over 3 r cubed sine theta from 0 to 2 d theta. And now we get, let's see, that'll be 10 minus 8/3 sine of theta. Everything else is 0. And so this is d theta. And so now this is, now we take the integral of this. This will be 10 theta minus 8 over 3 cosine, so it's plus cosine theta, 0 to 2 pi. All right, so that's 10 times 2 pi plus 8 over 3. That 0 will take care of this. Will be cosine of 2 pi minus cosine of 0. This ends up being 0, and so this is 20 pi. And that's the answer. All right, so the lesson here is that you don't need to necessarily make this first one dz, all right? It's whatever is most helpful. If more things are changing in the y direction than the z direction, then you do dy first, or dx. It just depends on the problem. Okay? So hopefully that makes number 22 a little simpler.